Welcome to episode 7 out of 7. Thank you for staying tuned as we've been demystifying Northwest Mock 2023. Please stay tuned and make sure to watch all our previous videos. Enjoy.
So yeah, guys, just pause the video, go ahead, check it out, and see if you can do it. Let's go. So state the experimental results of photoelectric effect. Guys, I'm just really going to quickly state them. Emission is instantaneous. Emission does not occur until the frequency of the incident radiation is greater than the threshold frequency. The maximum Ke of the ejected photoelectrons is proportional to the frequency of the incident radiation, but does not depend on the intensity of the incident radiations. I'm just really stating them, guys. The number of photoelectrons ejected per unit time is directly proportional to the intensity of the incident radiations. And the Roman 2 says use Einstein's photoelectric equation to explain each of the observations. Okay, photoelectric equation E equals HF0 plus EK. So you realize that emission is instantaneous because once an electron absorbs a photon of sufficient energy, it is released. All right, good. So that's it right there. Then if E is less than HF0, emission does not occur, while if E is greater than HF0, the excess energy over the work function provides kinetic energy for the electron to escape. Okay, yeah. And then one photoelectron is produced when a photon is absorbed. Thus, when the number of photons hitting the metal surface per unit time increases, the number of photoelectrons per unit time increases too. That's the point why you would increase intensity, and that increases the number of photoelectrons that are ejected. So that's what the explanation there. Okay, so the next part says a composite bar is made of this. All right, so solve that quickly. Dq dt is Ka delta theta on L. So dq dt across x will be equal to dq dt across y, okay, at steady state. So dq dt across x across kxa, change in temperature of x 100 minus interface temperature divided by 25 equals kya 60, really. Okay, so ky on kx is what? It's 3 times 4 60, and so we get that ky on kx is 2. Right, so that's really easy. You're just really using this equation, and then you're sort of seeing what is really happening, and then yeah, simplifying. So F says state Coulomb's law of electrostatics and Faraday's law of electromagnetic induction. So Coulomb's law, the electrostatic force of attraction or repulsion between 2-point charges is directly proportional to the product of their charges and inversely proportional to the square of the mean distance between them. Faraday's law of electromagnetic induction, the time rate of change of flux that is linked to a coil is proportional to the induced EMF across it. Okay, so electric potential, the work done per unit charge in moving a charged particle from infinity to that point in the field. Roman 3, we want to calculate the work done in moving a particle from A to B. So work done is normally Fx, right? But what is F? Force in electric field is basically EQ, okay? So E here, since the uniform field, is basically V on D. So V on D there is my E multiplied by Q times X. So my work done there is my V is 1000 volts, remember, 1000 volts divided by my D, which is 10 millimeter, multiplied by Q. Q there is 10E because there are 10 electrons there, okay? Drop carries 10 electrons. So that's the charge right there. And then you multiply that with our X, and our X is simply this small distance we're moving, 5 millimeters. So if you simplify, your work done is simply 8 times 10 to the negative 16 joules. That's it, and that's how much energy you transfer.